I'm just going to go through a few examples to bring these diagrams, these flowcharts, a little bit more to life. So first off, let's look at this system where there's a really dominant hill slope or set of hill slope processes that are occurring in the background. So what we see is this big flat top right here, and then there's this steep wall or steep kind of cliffy edge over here, and then you can sort of see it roll over into this still steep but a little bit more gentle topography, including some of these zones where you see these what look like, well, I'll just use the word tributary. So these little tributaries coming together, and you see the same thing over here. And so there are steep walls and then some lower relief parts. And so there might be some fluvial related processes, so some water erosion related processes going on here too. Over here you see this kind of lower relief fan coming out from the side of the hill slope. And then in the foreground you see these kind of gently undulating bumps, including this bit of tallgrass prairie that the viewer is standing on. And so going from the viewer back to the hill slope, back to rather this big hillside. So it's not totally clear what's forming each of these bumps in the foreground. One guess that I might have is that perhaps they're built by aeolian processes, so by sands that are blowing, and then they're later stabilized. Another guess is that there's some sort of larger system of ephemeral river channels flowing from the west side to the east side of this image, and that those are slowly eroding out this landscape and cutting through bedrock. How would we know that? We could look at the larger scale topography and see if something is similar to sand dunes or similar to a drainage pattern. Or we could go out in the field and start taking samples of the material and seeing, does it look like dune sand? Is it fine and well sorted, meaning that it's all about the same size? Or does it look more like deposits that are associated with rivers, and or does it look like bedrock? As we move farther back into the system, we can see these valleys and these steep walls, and so there might be some landsliding happening over here on this really steep face. So that's another hill slope process. And then over here you can see, there's some more rounded hills. You can also note that there's a difference in which on one side you might see a little bit more vegetation, and the other side you might see a little bit less. And in that case, typically in what looks like an arid environment like this, the vegetation will be on the side that is facing the pole. So the pole is going to be over on this side of the image. And so in that case, because this is in Wyoming, this is probably north over here. And then on the very top, this big flat thing, we could typically call that a cap rock. You can see some of it exposed here. And that means that this is a difficult to erode rock unit. So it might be hard. It might have very few joints where it's broken. And that means that it's able to exist at the top of this hill without actually breaking down very much. And it essentially is protecting the hilltop from erosion, so this hill can only erode in from the sides and slowly undercut this rock and break it down, but is not going to be so quickly approaching erosion all the way to the center. And so this is a pretty classic plateau style surface. Next, and in fact this is the last thing that we're going to do, I'm going to take you through a little tour of many process domains that are existing within a single landscape. And we're going to hop over to Jasper National Park, where just a year before this recording or so, I helped my friend Billy Armstrong, a professor at Appalachian State University, so in Western North Carolina, do some of his research on the Athabasca Glacier. So this is a picture. Billy's on the right. His weather station is over there too. And so we're in the Athabasca Glacier, Alberta, Canada, and looking for multiple process domains within this single image. So I just wanted to show you, right, obviously this is a glacial process domain, right? So there's a glacier, which I've marked in the middle. All of these things over here on this side of the valley, these are glacial moraines. All the things that look like they have these big, deep incised rills going through them. And so that's the way that these glacial moraines are eroding as the ice within them is melting, as water is flowing through them and over them. They develop these steep channel networks. And that, in fact, would have occurred in places in the Midwest, too, prior to the time when the moraines were vegetated. Over here, you see these big bedrock cliffs over there and over here. These were covered by ice at some point in the past, and that ice cover plucked blocks off, so quarried whole blocks and carried them down valley and eroded them that way. And so glaciers can either abrade rock into smooth faces, or it can pull whole chunks off. And in fact, rivers do the exact same thing. So closer to us, I have this thing labeled debris-covered ice. So it looks like a big field of just rocks and gravel, but this is actually a relatively thin veneer on top of ice. And this is the way that a lot of glaciers are going to become if global warming persists, is that they are going to actually hide under an insulating blanket of rock that they erode from their own landscapes. And that's going to, in fact, reduce their melt rate. And so they're going to retreat and effectively stop looking like glaciers. But then their retreat rate is going to be slowed down a bit as they bury themselves beneath the rocks. And so you can see right between the D and the I, there's a steep thing. And this is an ice face. And so this is the main way that debris-covered glaciers will, or one of the main mechanisms by which debris-covered glaciers will waste away, is as these ice faces retreat, because these are zones where you're actually cutting through that insulating blanket of rock and exposing the fresh ice. And Billy and I are sitting up on a moraine right here on which the weather station is perched. There's another glacial moraine, this little hill right down here. And as the glacier retreats, it forms these moraines. And so we know that the one that we're on, this big one, is older than this one that is a little bit closer to the ice. As we go down valley from that, we started working to gauge the stream to see how much water is melting off of the glacier. And in fact, so this is a laser rangefinder gauge up on the top of the cliff that's built in my lab and that we installed out there. So on the upper right, we can see this bedrock. And so I was showing you this Hackley bedrock before, this bit that was eroded by big block removal. This is a smooth, glacially abraded bedrock right in this kind of, if we say that north is up, this northeastern corner of the photo. We also have fluvial incision into the moraine, so you see this kind of brown, buffy colored material. So this is all glacial moraine on this side and on this side as well, lapping up against these rocks. And as the river cuts down in sizes and removes it, it can remove that fine material really fast. That's why the stream here looks like it has such milky colored water. That's all of this glacially eroded material going down channel. And then it has a little bit more trouble eroding the larger material, which it has to carry along its bed, and will, at times of lower flow, such as this, so this is in the fall, will deposit into bars. These bars exist underneath the surface of the stream while it's flowing at its full discharge as well. But when the stream is flowing at its full discharge, these bars might actually have sediment that's mobilized instead of just sitting there. And of course, as the river incises into these hill slopes, it creates steep slopes, and we can see the one in the foreground quite nicely. And those steep slopes can erode pretty easily just by the action of gravity or any sort of animal walking across it, or a couple scientists trying to put in some instruments. And that material will tumble down the hill slope and into the river. And so the river and the hill slope are interacting directly here, with the river cutting down and creating a steep slope, and the hill slope responding by eroding and sending extra sediment into the river. A little farther downstream in the river, we can combine these coastal and fluvial systems. And so coastal, I say in quotes, right? Because this lake is not a whole lot larger than this river delta right here. But nonetheless, it's a standing body of water, and this is where this proglacial stream is depositing all of its sediments. And you can see even on some of the zones that are a little bit farther from the areas where the river is actively reworking, by which I mean eroding and depositing sediments, some small amount of tundra vegetation has managed to take hold. So just to kind of sum up some of the main things that we've discussed here. So these geomorphic process domains are something that we use to split the landscape into zones with connected sets of properties and processes. So you can think about this as connected sets of landforms and connected sets of physical, chemical, and biological processes that have formed them. In these examples, we focus mostly on the physical processes, and that in fact is pretty common in geomorphology. But we can't forget about the chemistry or the biology as well. And it might just mean that some of those are topics for future research that haven't yet gone in textbooks. Although we do know quite a bit about chemical processes in soils and biological processes affecting the coasts. So these process domains also interface with one another. Process domains such as, we're seeing the fluvial and the hillslope systems on top of glacial deposits. They also provide a way to map conceptual and mathematical models, which you might have learned about just a little bit before if you watched that video, onto landforms and the processes that change them. And so if we can connect these landforms and these assemblages of landforms and processes into groups, we can then start to create some hypotheses about how they might change and what might drive that change. We can test those hypotheses in the field, lab, and with computer models. And in order to build computer models, we need to then convert these conceptual models into numerical models, which are a computer's version of a mathematical model that we can use to see, is our conceptualization correct or is it falsifiable? So with that, this is just how we break down the landscape, and this is the best way that we have right now as geomorphologists for trying to understand these individual pieces, and eventually we're going to put them back together.